All right, good morning. Time for another video, and I'm doing a several-part series, and this is the fourth part on a series I'm calling The Impossible Mathematics of Atheistic Materialism and Evolution. And we're going to discuss some of the I've discussed proteins quite a bit. I'm gonna cover some of that, but then I'm going to get into a new area I've never covered, and that's the interactomes. And I'll use quotes from peer-reviewed papers and video clips talking about proteins and the interactomes. And then I'll prove it to you that the actual scientific evidence points to mind, not random universe land. So let's start, though. We're going to do a short review of some of the previous episodes in the series. And so part one, I discussed DNA for first life, and it's still my contention, and I'll get into this later, for some of the proof about why I think about 400 million lines of DNA of software code is needed. Well, after I get done with the protein side of it, you'll see why I say it's 400 million lines. I'll bet you it's way more than that. I'll bet you it's into the trillions by now, because DNA is responsible for a whole lot more than just the proteins. But anyway, then we got into what I would call before RNA and then post RNA. After you get RNA, you still got to get to the cell, and we went round and round about this. It really hadn't been my intention to spend all this time on, quote, information, but in a good way, thanks to the atheists and their insistence on RNA is your daddy. Well, he's not my daddy. It's hogwash, and you can go watch the videos and read the comments. It's hogwash that you would believe that RNA is your daddy, but you have to go there as an atheist. You have to go there now. Why? Because the first cell is too complex to have come about by chance, period. And we're going to even add more and more complexity to it, and that's what part 4 is about. It is beyond your wildest dreams, and we're going to discuss it. In fact, not only is it beyond your wildest dreams, you don't have enough time, and I'll prove it in the video. So one of the articles I'm going to talk about says that it's the Leventhal paradox of the interactome, and here's a quote from the article that I'll talk about later in the video. The central biological question of the 21st century is, how does a viable cell emerge from the bewildering combinatorial complexity of its molecular components? Believe me, that term, the saying, bewildering combinatorial complexity, goes nowhere near describing what we're talking about. It is way beyond chance, way beyond it. But first, what's going to follow is a short summary of some of the facts that I've presented in the past. I'm talking mathematical facts in regards to proteins. Okay, so first, though, I want to caution you about something. Look, don't get bogged down in all the science. I'm not asking you to understand it all. I'm not. You don't have to understand it all. All you have to do is ask yourself, how could this much complexity come about by chance and in only 10 to the 18 seconds, which is 3.6 billion years? In fact, I'll show you later on, you don't have that much time. You have nowhere near that much time. So, facts about the number of proteins needed for a one-cell creature. First life, which would be abiogenesis. Well, it's official. There are some 42 million protein molecules in a simple cell. You go, say, what? Yeah. 42 million protein molecules. Okay, you say, well, so what? Well, another fact that I want you to get in your head. Some of those protein I said cells, I'm sorry. I always do that. I'm not confusing the two. It's protein molecules, but I'm always conflating molecules and cells. Sorry about that. But 42 million protein molecules, and then some of those protein molecules, you need like 10 copies of them for a specific organelle in the cell. And in other organelles, you need up to 500,000 copies. 500,000 copies, all at the same time, for a specific structure in the cell. Origin of life scientists, researchers have calculated what they would consider the minimum number of protein types, not the minimum number of proteins, the minimum number of protein types of proteins that they need to build the first cell for abiogenesis to be true. And let's just put it at about 200. They say it's about 206, so let's put it at about 200 just to round it up and to be nice. Now, according to the previous quote, so some of those proteins are going to need 10 copies of themselves, and others of those 200 proteins, they need 500,000 copies of themselves. Well, Proteins, this is what makes it complicated, are made up of amino acids in long polypeptide chains. And there are 20 types of amino acids that make up each position. So a protein molecule, you can visualize it like a biclock, like I show you here. And in this particular biclock, they have 4 dials and 0 through 9. Well, in an amino acid, you would have, let's take a small amino acid of 150 amino acids long. Okay? So what you would have is you would have a biclock with 150 dials. But instead of 0 through 9 positions, you would need 0 through 9 and then A through J for 20 positions on each dial. So 150 dials with 20 positions per dial. Some protein molecules are up to 1 to 2,000 amino acids long, and therefore you would need a biclock. It would be a biclock with 1 to 2,000 dials and 20 positions per dial. And the sequence is, as we'll see, very, can't say very enough, important. Okay, so not only do you need the proteins also, though, but then you also need nanomachines. But what's interesting about the nanomachines are made of proteins. And the nanomachines are necessary for the creation and the synthesis of proteins. So you have the ultimate chicken and the egg problem. Which came first? The proteins or the nanomachines made of proteins, needed to build the proteins. And one of the examples given in the previous episodes, we were talking about RNA so much. I found a quote on an article talking about how RNA only lasts for 2 minutes. And they screamed up and down, well, that's not true, that's not true. They wanted me to give them 48 hours. 48 hours? Oh my God, you're saying this stuff's sticking around in ponds for millions of years, and you're quibbling over 48 hours. Whatever. And I didn't write the article. I just said what it said, that it only lasts for 2 minutes, and yet they're telling me it's going to stick around in a pond for millions of years while all these trillions and trillions of pieces come together. It was total nonsense. Well, one of the reasons why it only lasts for 2 minutes is because of a molecular machine, RNases. They tear down RNA molecule. And to the atheists, that's a benefit for them, see. To me, it wasn't. Which came first, the RNases or the RNA? Which one? Other molecular machines for the production of proteins, and in no particular order, one of them would be the RNA polymerase. The RNA polymerase, what it does is it actually builds the messenger RNA, and the messenger RNA is the one that carries the genetic code from the DNA. It builds the RNA polymerase, builds the RNA molecule from the gene in the DNA from the DNA molecule, okay? And it's the one that has the information. Well, all cells have monster molecular machines called the ribosome, which is a nanofactory, which builds each protein molecule. But the factory is also made of proteins. And if you'll look at the picture there, that is a picture of a ribosome. And it itself is made of proteins. Which came first? Then you have transfer RNA, another molecular machine. Well, what does it do? Well, it brings the amino acids to the ribosome factory. Again, the ribosome is a huge factory to build each protein molecule. And it used to be, when I first started doing this years ago, there was not much debate. I learned that protein folding, a protein is assembled in a long string, but it has to fold up. And if it doesn't fold up correctly, it will not work. It will not work. And as we'll see, the folding of the protein is very, 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 very specific. Anyway, when I started, there was no denial that other nanomachines in the cell themselves made of proteins also helped in the folding of proteins. And then it was supposedly discovered that no, proteins fold themselves. Well, recent studies say no, that's not true. So now we're back to the fact that the proteins don't fold themselves. They need other nanomachines, say called chaperones, so to help the proteins fold. So that's just 5 so far of the molecular machines a cell needs for protein synthesis. And they They have to be there. They're already there for all of this assemblage. So now let's make it a bit more complicated. And here's a quote. Every living cell, even a single bacterial cell, can be thought of as a gigantic chemical factory. DNA patterns or genes exert their effects by influencing the course of events in the chemical factory, and they do this via their influence on the three-dimensional shape of protein molecules. The word gigantic may seem surprising for a cell, especially when you remember that 10 million bacterial cells could sit on the surface of a pin's head. But you will also remember that each of these cells is capable of holding the whole text of the New Testament. There's your DNA. And moreover, it is gigantic when measured by the number of sophisticated machines, nanomachines, that it contains. Each machine is as a large protein molecule put together under the influence of a particular stretch of DNA. To get an idea of the size of these protein machines, each one is made up of about 6,000 atoms, which is very large by molecular standards. There are about 1 million, get that, 1 million of these large pieces of apparatus in a cell, and there are more than 2,000 different kinds of them, each kind specialized to do a particular operation in the chemical factory. And guess who wrote that? The high priest of atheism, Richard Dawkins. Thank you, Richard Dawkins. Sir Fred Hoyle, one of my go-to statistics. Any probability greater than or equal to 1 chance in 10 to the 50th power would constitute a miracle. And you'll see in a moment that the numbers are astronomical. But here's a side note. While I bring this up, the atheist, he just, in some of the comments, he brings up a deck of cards and he goes, see, a deck of cards is a miracle. It's like, what? It's misdirection, obfuscation. Take a new deck of cards. A new deck of cards usually comes in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, 10, Queen, King, Ace, whatever. And in the same suit, right? Like they'll put them in like the hearts, diamonds, spades, and clubs. And it'll be all in one way. Now, if you take and you forget about the jokers. So you take that deck of cards and you start shuffling it. What's the chance of you ever getting it back to the original order that it was in? Well, that chance is 1 chance in 8 times 10 to the 57th power. Again, my miracle is 1 times 10 to the 50th power. Now, this is what the atheists didn't point out, and I'm going to point it out. A deck of cards, the first time they made a deck of cards was like in the 14th century. So this mathematician said, okay, let's go 800 years before that time. And so the year was 1223. That's 800 years before they came up with a deck of cards. And then let's assume at that time, all the way up to this time, there were 8 billion people on the planet. And they're doing nothing but shuffling, all 8 billion people, once a second for all this time, all the way up to today. Well, that would give you a total of 2 times 10 to the 20th power only possible tries to date, which only means, as you can see the figure on there, blah, blah, 0.0000002% of the orderings have been seen so far on this planet. Well, that's nothing. I mean, that's nothing. So it would be a miracle. It would be a miracle if you shuffled the deck and the deck went back to the exact order you took it out of the pack when it was brand new. In fact, if you ever shuffle the deck and turn it over and it's in the order of the pack as it was when it was brand new, you definitely are cheating. Period. So it's not a good example, and you lose. Anyway, the chance of one small protein molecule of only 150 amino acids coming together by chance is 1 chance in 10 to the 77th power. And another atheist rightly pointed out something. That's 10 to the 27th power greater than 1 miracle. 10 to the 27th power greater than 1 miracle. That's amazing. So, as we've already seen, a small cell needs 42 million protein cells. I mean, again, I got cells. See? A small cell needs 42 million protein molecules. Sorry, I keep doing that. So a small cell has 1 million molecular machines, or they call them enzymes, and they're built from proteins. And now, something I've never presented is on its way, the Interactomes. Let's watch a short video clip.
We just don't know how. And even if we had all the pieces, we wouldn't know how to assemble them into a cell, because there's so much alignment that is needed. Not just the covalent detachment where one molecule hooks to another, but the non-covalent interactions. These are two molecules wanting to come close in space to each other. There's an ordering to these in cells that is highly complex that we didn't even know about until, I don't know, 15 years ago or so. It's called the Leventhal 2.0 paradox. How do you get this ordering to go, the non-covalent ordering? The numbers are utterly astronomical as to the combinations that one could come up with, and only a few of those combinations are going to work. That's it. Interactomes. This is the non-covalent interactions that function within a cell. Nobody knows how a viable cell emerges from massive combinatorial complexity of its molecular components. And of course, nobody's ever synthetically mimicked it. An interactome is the whole set of molecular interactions in a particular cell. If one merely considers protein-protein interaction combinations in just a single yeast cell, the result is an estimated 10 to the 79 billion combinations. That's estimated by these folks at Johns Hopkins and Brussels, all right? That's not my estimation. These are biophysicists, all right? So just to give you an idea of how big that number is, that's 10 to the 90th is the number of elemental particles in the universe. That's 10 to the 90th. This is 10 to the 79 billion. That's a big, big number. And the Leventhal 1.0 paradox was, how do you take a chain of amino acids that is now a polypeptide and have it fold into the right shape it has to be an enzyme? Because you need other enzymes are called foldamers, which will fold that enzyme that you want into the right structure, because there's too many variations on how these things may hook up with one another.
And that is not nearly as hard as the problem of hitting this dot to get one of these protein folds right. The number, if you want the probability for getting the protein fold, is 1 in 10 to the 77th power. That's 1 in a trillion, 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 trillion. A little bit worse than that, but I got tired of saying trillions. So it's like having laser points, laser dots the size of hydrogen atoms. That's a very small laser dot. And the ceiling would be the size of the backdrop of the visible universe. Okay? All right? Think about that. One dot, hydrogen atom, hidden at the backdrop of the visible universe, and something blindly searching that huge shell, hoping that these two hydrogen atoms, oh, you were close. You were so close. But it's just not going to happen. Obviously not.
Interactomes, Leventhal's paradox. So in 1969, Cyrus Leventhal noted that because of the very large number of degrees of freedom in an unfolded polypeptide chain, in other words, a protein chain of amino acids, the molecule has an astronomical number of possible conformations, the ways it could fold. An estimate is 10 to the 300 was made in one of his papers. For example, a polypeptide of 100 residues, that means 100 amino acids, will have 99 peptide bonds, and therefore 198 different phi and psi bond angles. If each of these bond angles can be in one of three stable conformations, the protein may misfold, that means not work, that means not be viable, that means it wouldn't work and be good, may misfold into a maximum of 3 to the 198th power, which is 2.95 times 10 to the 94th power. Different conformations, including any possible folding redundancy, and that's only one of 100. Okay, so that's larger. Mine is 1 chance in 10 to the 77th power. This is 2.95 times 10 to the 94th power. So conclusion, and here was their conclusion. Therefore, listen, this is what's important. This is what you should remember. If a protein were to attain its correctly folded configuration by sequentially sampling all the possible conformations, it would require a time longer than the age of the universe to arrive at its correct native conformation. What does that mean? Well, out goes random, universe land, period. And now here's quotes from a peer-reviewed paper. A polypeptide chain which is what a protein is, could not arrive at its native structure in biological real time by random search because conformational space is far too vast. Our goal here is to show that assembly of the interactome in biological real time is analogous to folding in that the functional state is selected from a staggering number of useless or potentially deleterious alternatives. In fact, if some proteins fold incorrectly, it causes all kinds of health problems. It is bad. So, given the time required for single bond rotations in picoseconds, by the way, picoseconds, that is a very short amount of time, even a small protein that initiated folding by random search in picoseconds, by the way, at the time of the Big Bang would still be thrashing about today if it could change its shape into different conformations within picoseconds. It would still be thrashing about today. So in this case, the estimated number of different interactomes is on the order of 10 to the power of 7.9 times 10 raised to the 10th power. Just like James Tour said. 79 billion. My God, that's a big number. The numbers preclude formation of a functional interactome by trial and error complex formation within any meaningful span of time. This numerical exercise, a Leventhal paradox of the interactome, is tantamount. Listen to this. Is tantamount to a proof that the cell does not organize by random collisions. Random, universe land is now dead. So, the Leventhal paradox, and as James Tour noted, there was 1 and 2. This is more like paradox 1, but that's okay. Short answer, what is the Leventhal paradox? It is not really a paradox, but more the apparent mystery of how the cell repeatedly is able to pick the correct way to fold a protein, avoiding an unimaginably high number of possible wrong ways. The mystery involves the impossibly low probability for a protein to be properly folded after polypeptide synthesis by ribosomes. The number of possible folding conformations are beyond astronomical. A 100 amino acid polypeptide can be folded 10 to the 140th power different ways. See, mine was 150 amino acids long, 10 to the 77th power different ways, whatever. Much of which lead to a misfolded useless protein. Okay. And, I'm sorry, one more thing. Still, post-ribosomal processing produces perfectly folded proteins in milli or microseconds. And, of course, it said earlier in picoseconds. Okay. So can you say, wow, I know that was a lot of data, but what did we just witness? Let's break it down in real easy to understand terms. Okay, interactomes were discovered only about 15 years ago. And there are 10 to the 79 billion combinations possible. Yet, as James Tour said, only a few of them work. So that's what's important, the combinations. And my go-to statistic, any probability which is greater than or equal to 1 chance in 10 to the 50th power would constitute a miracle. So just one small protein of 150 amino acids long is 1 chance in 10 to the 77th power. Yet a small cell needs 41 million protein molecules all at the same time. All at the same time. And now 10 to the 79 billion possible combinations for the protein-to-protein interactions in a yeast cell, no less. And only a few work. So my question is, how much evidence do you need that the cell was designed by an unfathomable mind? Random universe land is in big trouble these days. The math doesn't lie. The math does eviscerate chance as an explanation of how life got started. Just the formation of one protein by chance eviscerates abiogenesis. And now, 42 million proteins encoded from the DNA strand. So question, how many nucleotide bases need to be encoded to program just the 42 million protein molecules needed for the first cell? It was my contention in the first video, which they balked at, was 400 million lines of code. I think it's a reasonable estimation based on 42 million protein molecules. And those molecules are made up of amino acids, and some of those molecules are 1 to 2,000 amino acids long. All that information has to be encoded in the DNA for the RNA polymerase to then build the RNA molecule to build the proteins by the ribosome. And that's just the proteins. Now we have to add another number so large, 10 to the 79 billion possible protein-to-protein combinations, and the vast majority of them would result in failure. Not even the entire age of the universe is enough time for one chance combination of the interactomes. In fact, you don't really have that much time. The Gesso story is that 3.8 billion years ago, the supposed first life emerged after the late bombardment when no life could exist. So really, you only have a few million years now. Now you're down to just a few million. And yet the papers said point blank, there's not enough time in the entire universe for not even one interactome, for not even one protein fold. The entire time that the universe has been here. So irregardless, at this point, I mean it, it is sheer, willful ignorance of the mathematical, computational facts that I've given that convinces you that God is not responsible for life on this planet. And that is a simple, scientific, mathematically verifiable fact, as I have shown. It's only getting worse and worse for the atheist as time goes by. And as more is learned, the goalposts again. They're past the Andromeda Galaxy, speeding away from you faster than the speed of light. And that's a fact. That's a scientific, mathematical fact based on proteins and the interactomes and the DNA and the complication of even getting to RNA first and then getting from RNA to the cell. Trillions and trillions of ways that it would all go south. All of that's the truth. Enough said. Have a blessed day. Bye.